Hello everyone, and welcome to the second installment of Helpline Bling. Today I'm wearing my Drake sweater, and if anytime you have a question, you can get on that Remind app and let me know. I'm in a boring meeting and don't mind being interrupted, number one. Number two, you're probably thinking to yourself, oh my god, we have a test on Friday. Is this going to be on the test? Generally speaking, yes, it is going to be on the test. I'm going to review this Friday morning, but here are the things that I kind of want you to know. I want you to know about these periodic trends. When looking at the periodic table, these different trends, these different patterns that emerge. And we'll be talking about atomic radius, ionization energy, electron affinity, how they're related, stuff like that. So let's jump right into it. Effective nuclear charge. All right, so we're going to be talking about an atom here. And this atom is going to have 11 protons. So if it has 11 protons, what atom is it? Anyone? Anyone know what atom it is? Come on, you in front. Awesome. Let's look at number 11. It is sodium. So we're talking about sodium right here. So sodium has, and if you were to draw it out, 11 protons in the nucleus. Awesome. And then you would draw out the different energy levels. In the first one, there'd be 2. In the second one, there'd be 8. And in the third one, would be 1, right? This is the third energy level right here. It's in the 3s, right? So all of these periodic trends and tables correlate to this effective nuclear charge. And this effective nuclear charge is because electrons on the outside, this valence electron is pulled in. It's pulled in because of the protons right here, but it's also pushed away because of the electrons in the middle. So basically the protons say, get over here, and the electrons say, no, and you can calculate this, all right? And its calculation is basically based on the number of protons and the number of core electrons. And when we're talking about core electrons, we're talking about the electrons right here. Basically, it's the opposite of a valence electron. Valence electrons are on the outside, core electrons are on the inside, all right? Cool. So let's look at how to calculate this a little bit. Same one, all right? Talking about sodium over here. And we're going to say the effective nuclear charge is ZF, or Zeph. Wouldn't that be a cool name for a kid? Hey, Zeph, get over here. All right, stupid name, my bad. So ZF is equal to the number of protons, bam, 11, minus S, the number of screening, or the number of core electrons. So 11 minus 10 is equal to positive 1. The effective nuclear charge for sodium, which is represented right here, would be positive 1. Okay, cool. Now it's your turn to try. I want you to calculate the effective nuclear charge of valence electrons, so the outermost electrons, moving, ooh, I have to do this backwards because of the camera, moving across a period, across the row, for sodium, magnesium, phosphorus, chlorine, and argon. So pause, do that, catch up with you in a moment. Sweet. So first off, sodium, we've already done that. 11 protons minus 10 core electrons, aka shielding electrons, equals positive 1. Awesome. How about magnesium? Magnesium, 12 protons minus the 10. There's still only 10 core electrons. Go to positive 2. Bam, jump all the way over to phosphorus. 15 protons minus those 10 core electrons. You might have to draw these out, but you'll see a pattern in a second. 15 minus 10 equals 5. Chlorine, 17 minus 10 equals 7. Ooh, excuse me. And argon, 18 minus 10 equals 8. So you're probably thinking to yourself, okay, I get it. The effective nuclear charge increases from left to right, moving across the periodic table. It also increases slightly from the bottom up. And this has to do with the size of the electrons, okay? Ooh, notice here that the number of core electrons remain constant. That's because with that core is just that first energy level and that second energy level, or that 2 and that 8 as we're moving across the period. Whoops, whoops. Oh, that looked like one of those cool dance moves. Across the period, right? You would notice a mathematical change in the Zeph down a column, but it decreased slightly due to the valence electrons being further out. And we're going to talk about radius size in just a second. Okay, oh, this is it, radius size, just like I said. So let's talk about the size of atoms. As you can see here, helium, itty bitty little atom. Over here, super big atom. It increases going this way. Let's talk about why it's increasing, okay? So first off, atomic radii, I love that word, radii, it's the plural form of radius, and yeah, you can look it up. I know your math teacher probably says radiuses. But anyways, it's the distance from the nucleus to the edge of the electron cloud. All right? And as we move from the left to the right, that's backwards for me, it's increasing. And here's the reason why. The more and more protons we put in the nucleus, the more and more it's drawing in those electrons, right? So more and more positive charge, more and more bringing in, making the atomic radius smaller, okay? But if we add more and more energy levels, you would expect it to get bigger, right? So that's kind of what we see here. It gets smaller moving across because there's more protons sucking them in, but it's getting larger moving down as we're adding more and more energy levels. That makes sense, right? Right, yeah. All right. They have more electron shells, thus they get bigger. I just said that. Oh, here's a cool little drawing, or a little model. Here is the distance between the nuclei, split in half. Distance divided by half is atomic radius, and that's what we're talking about. Dope, dope. All right, ionization level. Ionization energy is basically the energy that is needed to remove an electron from an atom. So if we look at this one, let's figure out what this is. Oh, we got 2, then we got 8, then we got 2 more, so we got like what, 12? 12 is magnesium. So we're looking at magnesium real quick, okay? 2, 8, 10. Sorry, 2, 8, and then 2. So we can classify these ionization energies, and the ionization energy is the amount of energy required to remove an electron from an atom. So we're like, hey, give me that electron, mister, or missus, who knows? The first ionization energy is the energy required to move that first one. So I'm just saying, hey, give me that. Compared to the second ionization energy, which is the energy required to remove the second one. So if the first one is removing this one, bang, then the second one is moving this one, bang. All right? Cool. So this is related to the effective nuclear charge. All right? So again, we have Zeph is equal to, this is for sodium, 11 minus 10 equals 1. So the valence is being pulled in with a weak +1 charge. So that means that those protons, there's only a 1 difference between the protons and the electrons, and so it's kind of just like barely hanging on. You know what I mean? So it's pretty weak. But what if you were to calculate the effective nuclear charge for one of it, same atom, but for an electron that's in the second shell, the second energy level? All right? It would be 11 minus 2, because there's only 2 that are shielding it, equals 9. That's a crazy amount more, from 1 to 9. So removing that first one, if I go back a slide, removing like one of these electrons, not that big of a deal. Removing one of these guys, are you kidding me? No way. No way, man. Not going to happen. Not going to happen. All right? So the second energy level is 9 times as strong. Crazy. So which one's easier to remove? I kind of just told you that. Which one will have a higher ionization energy? Well, this first one is going to have a much lower ionization level energy. It will be easier to remove compared to the second one, which would be much higher. Okay, so as you move across, these are different ionizations levels. So if you're taking off the first one, taking off the second, taking off the third electron, taking off the fourth electron. So the sodium, you take up the first one, okay, bam, 495, not so bad. But look how much it is for that second one. And these ones, these blue ones, are these inner shell electrons. So it's like, all right, take an outer one, not so big. Bam, look how much it drops, it gets to remove the second one. You're not removing that bad way. No way. Here, remove the first one. All right, move the second one. Not too happy. Remove one from over here, from these inner shell electrons. Get out of here. Forget about it. All right, so trends in first ionization level. As you can see, not too bad removing these, but the more you move down the periodic table, the harder it's going to get. Remember, these guys right here, full octet rule. They are happy. They are stoked. They have all 8 of their valence electrons. You think they want to give one up? Heck no. All right? Same with these. They're so close. They're so close. So, ionization energy decreases from top to bottom. All right? This is because over here, those electrons are already so far away from the nucleus that the strength of the protons attracting those electrons is pretty small. Furthermore, valence electrons are farther from the nucleus. I just said that. Oh my gosh. All right. It increases from left to right. Talked about that. And this is because the increase of the effective nuclear charge holding the electrons tighter. Pretty much done that. Okay. Electron affinity. Electron affinity. So electron affinity is like the opposite of ionization. Ionization is taking an electron away. It's basically saying like how much is it holding on to the energy. But this one is how much energy it releases by getting an extra electron. So some of these atoms are really stoked to get an extra electron. They're so happy. Some of them could care less. These noble gases, they can care less. They don't really need any, right? That's why it's close to zero. But these guys, our halogens over here, they're so close to getting that octet rule. They're so close that they will actually release energy. They'll be like, yay! And they'll release all their energy. They'll party if they get that extra electron. All right? So electron affinity is the energy released by the addition of an electron to an atom. So moving from left to right across the periodic table, the electron affinity increases. All right, that means that's because these halogens are so stoked. These guys over here, they can kind of care less. You know what I mean? They're not too stoked on it, but these guys are so stoked. These guys are pretty stoked as well. These guys are so stoked. All right, and also top to bottom on the Petris, this increases as well. All right, let's see that. This is explained by the octet rule. If an atom is close to the octet, then it will be more likely to take on another electron. Now we're going to talk about reactivity, the ability for these elements to react. We have like these hot zones. Look at this, hot zone. Look at this, hot zone. These bad boys right here. So we have so close to an octet rule, so close to the center of the atom. All right. These are so thirsty. These elements are so thirsty. They want that electron. It's going to get it. And so these are super, super reactive. Likewise, these down here, they've got this extra electron, just one extra electron, just chilling way away from its proton. So they're going to probably get rid of that electron. All right. So these right here, super reactive. These right here, super reactive. And in the middle, not so much. They're not very reactive. All right. I just talked about this. Halogens, super reactive. Alkali metals, reactive. Noble gases, unreactive. Those noble gases already got their octet rule. They're cool. They're happy. The reactivity also increases if you go from fluorine down to francium. All right. This leaves the inert areas. Inert means it's the opposite of reactive. It means it doesn't want to party. It's cool. All right. It's going to throw shade. These ones right here in the noble gases. All right. So recap. Bam. Effective nuclear charge towards fluorine causes increased ionization level, increasingly negative electron affinity, smaller radii, higher reactivity. Decreasing effective nuclear charge towards francium causes increased metallic character, increased atomic radii. Bam. This is what you should know right here. Atomic radius gets bigger over here. Ionization energy and electron affinity gets bigger that way. All right. That's that. All right. Cool. It's been real. Let me know if you have any questions. Friday, we got a test. I'm going to cover this again, answer any questions. The things you should know for the test. Number one, how to do those conversions from grams to moles, moles to atoms, atoms to moles, that kind of stuff, and do the double conversions. Number two, periodic table and the families. You're talking about like the metals, the nonmetals, the rare earth elements, the noble gases, the halogens, the alkali metals, all those kind of things. And then from today, these general trends. I will talk to you later. Helpline bling. Deuces.